All right, dude, we are live. What's up, guys? This is Dem Keys, and today we are going to be doing another electronics stream, another ESP32 stream, and we are going to be focusing on potentiometers today. Um, so, between yesterday and today, I had a bit of a development. I was so I had this doubt that maybe along with the DIY self-tracking robotics car kit that I bought, I actually bought two of them. I had a doubt that along with those two kits, they were both the exact same kit. I just bought, two of them just so I had more to play around with. I had a doubt that um, they probably came with something that resembled a potentiometer in some way, shape, or form, but I wasn't entirely sure. And so I opened up the those kits today, and I looked at those potentiometers, and it turned out they are actually potentiometers. More specifically, apparently they're called trimmer potentiometers or trim pots. Hold on, let me go to the Gemini conversation. Um, yeah, it's called a trimmer potentiometer. How do I show this to you? I want to show it on camera, but then the thing is so small that I'm gonna need to like zoom in big time. I'm not sure how well that's gonna work. Give me a second. Let me try. Let me give it a try. I don't know how well that's showing up. Another way that I could go about this is to show it through Google Images. And since I'm doing that, I might as well also look up photoresistors because that's another thing. That's the next thing I'm going to be talking about. So, trimmer, or let me just look up trim pot. Yep, this is the one. Then I have this as well. Give me a second. Let let this thing load up, and then I can. Oh wait, it didn't do the thing. I thought it was duplicating the tab. But yeah, I've been busy playing around with that. And another thing that I'm excited about is I started using the modular breadboards that I had. I have these three small modular breadboards that you can like connect together in different configurations. I have two others as well. Let me show them here. One of them I have been using so far. Hold on. So those are the two breadboards that I have been using so far. Unfortunately, they are of different um I'm not sure what words to use here. I was about to say they're of different configuration, but it's more like their designs are different because what makes these things modular is hold on, I'm gonna have to try and show the detail here. If you look at the breadboard here, hold on. I need to open up my OBS. Okay. If you look at the breadboard here, on the side of it, there are, I guess you can call them notches. I don't know if if the notches are showing up very well. I'm not sure how to show it, but if you can see it, there are notches. There are three notches actually. Maybe the third one you can't see, but there are, at least on cam, there's you can see two notches that are sticking out, and then on the other side, there's grooves that notches are supposed to go into. Wait, isn't the notch also? What something goes into? Basically, one side is protruding out, and um, the other side is sort of hollow. So when you have multiple pieces that are like this, you can kind of slot them together, and they fit like puzzle pieces. So they can like lock in together, and that's what makes them modular. Because of this, you are able to set them up in different configurations, kind of like what I've done here. If you look at the breadboard setup right now, there are three of these breadboards connected together, and I was able to set them up in like an L shape because I wanted to separate the potentiometers and, well, the two resistors. I wanted to separate them from the other breadboards, and in general, I wanted to have like a modular setup, so I came up with this. I think I might order more of these modular breadboards because I like this idea. I'm glad that I purchased these. Believe it or not, I purchased these a couple of years ago, and since then, I've rarely ever used them. I think one situation where I had used them was actually okay. I have had a couple of situations where I did use them for a little bit, but like not nearly as often as these kinds of breadboards, the longer ones. Usually because the longer breadboards allow me to kind of have everything on one board and like move the entire setup. But then now with these modular breadboards, I can still move the entire setup. Like, hold on, let me show you. See that? I can move the entire setup, and I can make this as long as I want. Um, as long as I maintain the proper connections. Like if you look at the red and blue rails, those are power rails on the breadboard. Because these are three separate pieces, so if two of the pieces that are sort of in parallel, not parallel, but like what do you call it, like one after the other? It's not adjacent. Basically, the breadboard on which the microcontroller is and the breadboard on which the three LEDs are. These two breadboards are the ones that I'm talking about. Their power rails are not connected together. So if I want them to be connected, I'll have to use like a tiny jumper to make the connection between them. And that's just one of the, that's a thing that you have to do because that kind of comes with that's the price of making things modular. Let's put it that way. Okay, now I was supposed to be looking this thing up, so let me look it up. Trim pot, that's one, and then photo resistor, that's another one. The photo resistor is also actually a couple of them came with the two robotics kits that I had ordered, so that's a huge bonus. That's an advantage. That's an extra thing that we can play around with. Um, so I'm excited for that. Give me a second. Let me bring the browser back so you guys can see. Give me a second. There. Okay. So this is what this is specifically what I'm talking about. You can see here it says 102. Mine is 103. Uh, Initially, when I read this, I didn't know it was numbers. I thought it was saying EOI or E01 or something like that. It turned out I was reading it wrong. It's 103, and this is basically it's kind of like reading um, the color code for one of the other resistors. In the other resistors you have, or with through hole resistors, you have color bands that help you determine what the resistance is. But in this case, you have this number where the first and second digit are just the digits, And the third digit is the number of zeros you need to add after that number. So in this case, if it says 102, it's 10 and then 00. So that's a 1K ohm resistor, a 1000 ohm resistor. Mine is a 10,000 ohm resistor. Okay, next. Oh, wait, let me also mention, so there's a couple of different designs here. Mine is specifically this one, the third one in the top row. Mine is specifically this one. And it's great because these legs, they fit into the breadboard, into the breadboard holes. I don't know if they're meant for the breadboard or not, but they fit in pretty well. And this is convenient because the connection, the contact, is much better than what I would be getting from a potentiometer. Like if I attached wires to a potentiometer and then connected that to the breadboard, I would be getting, I'm getting much better contact here. To be fair though, I don't know if the reason for that is that I did a horrible job of soldering the wires onto the potentiometer, because that's very much a possibility. That is absolutely a possibility. That specific potentiometer that I was using yesterday, I didn't do a great job of soldering on it at all. I was very disappointed with the job. Okay, unfortunately, the stream crashed, but we are back. I have no idea what happened. The OBS just froze all of a sudden, and by the time it unfroze, I guess the stream actually no, it froze and then it unfroze, but it didn't really unfreeze because the UI was still frozen. It just looked like it unfroze. Um, but then when I tried to interact with the UI, it wouldn't work. And by the time I realized that, the disconnect protection ran out and the stream crashed. So I'm going to have to stitch the past 12 minutes of footage with this stream, which is fine because now I kind of have it, now I kind of have a workflow down for stitching VODs together in those rare situations where the stream crashes. But yeah, it is what it is. Okay, so where were we? We were looking at trimmer potentiometers. So the specific one that I have is this one, the third one. I don't know how well you can see it on stream because, well, the camera isn't like really zoomed in on the breadboard, and also the breadboard is not occupying the entirety of the screen. It also seems like it might be a little dark. I'm not sure why I'm getting that feeling. Um, Give me a second. I wanna try something here. Okay. All right. I don't know if that improved anything. I hope it improved something. Um, yeah, I don't know. I don't know. I'm not sure. Yeah, dude. I I can't tell. I'm not sure. It kind of seems like what's being lit up is the bottom left of the tissue area, which is actually not it's not helping in any way. Like lighting that up is not helping. Something I could do is okay. So here I've tried to like turn the light, so it's now focusing a little more on the rest of the circuit. I don't know. Maybe I'm just hold on. Let me increase the brightness of my phone screen and see if maybe I'm just making a big deal out of nothing. Yeah, I don't know. I'm not sure. Um, I'm not sure. Yeah, dude. I think I'm just gonna leave it as it is. Oh, that definitely became a bit darker. Hold on, I need to like crank up the brightness on my screen on my phone screen. You know what? Okay, I think I'm just making a big deal out of nothing. It is what it is. It is what it is. It's fine. I don't want to obsess about it too much. Yeah, yeah. I don't want to spend too much time on that. Okay, now give me a second. Let me just reposition my microphone. Okay. Now, the next thing that the next thing that I want to show you guys is a photoresistor. So this is a potentiometer. Actually, I showed you the potentiometer. I didn't show you the thing in action. I'm so what I'm going to do is I'm going to this is one of those potentiometers that actually let me come back to the browser. So if you look at the third potentiometer here, or literally any of these trim pots, if you look at uh, trimmer, that's a good way to put it. Yeah, yeah. But yeah, if you look at any of these trim pots, you'll see um, the place where you're supposed to be turning. It's not a knob. It looks like a screw. So you can like put a screwdriver in there and turn it. That's how you adjust these potentiometers. These, unlike your conventional potentiometers that have these knobs that you turn, unlike those potentiometers, these potentiometers are meant for more of a set and forget kind of thing. So if you have any circuits that require that could require some sort of tuning in terms of resistance or some kind of like calibration or something, then you would use this kind of a potentiometer because you would tune the thing and then you can just forget about the circuit at that point. At any point in time, if it needs to be tuned again later on, then you can tune it again by using a screwdriver or something, and then you're good to go. You don't need to have a knob exposed to the outside to continuously keep tuning. It's not meant for those purposes. I'm using it for one of those purposes because that's a lot more convenient for me. I'm actually considering buying a couple more such potentiometers. Dude, you know what I want to do? I wanna go look up all the different types of variable resistors that we can buy, because there are a lot of different types of variable resistors that you can buy. And I think potentiometers are one such variable resistor, but there's a couple others as well. Also, there's variable capacitors, which is an interesting concept. I haven't dealt with even just regular capacitors so far, so I don't wanna touch that until I don't want to touch the variable version of it until I've touched the component version, like the static version of it. For the time being, I have this potentiometer, and I want to look into the various other types of variable resistors that we can get, potentiometer or otherwise. Oh, yeah. Let me demonstrate the potentiometer in action. So this potentiometer, this trim pot, is connected to the red LED on the breadboard. The red LED, which is nearby the green and blue LEDs. I don't mean the red LED of the ESP32. I mean the three LEDs that are in the top right. So I'm gonna tune this trim pot, and you guys will be able to see the LED becoming dimmer or brighter. It may not go off completely because, for the sake of having a tiny bit of extra resistance, so that I don't burn the LED completely, I've also put in a 270 ohm, I think, resistor, just so there's like a tiny bit of resistance in there. That's why you can see the red LED lit up right now. And, well, actually, okay, to show you how bright the red LED looks without the trim pot, I'm going to disconnect the trim pot and just bridge the connection. Okay, so as you can see, it does become a lot brighter when I'm not using the trim pot. And when I am using the trim pot, then there's the resistor, the 270 ohm resistor, and also the trim pot's resistance, which is why you have like a already dim sort of light. So the idea is, when I take the resistance down to 0 on the trim pot, you'll see the LED becoming brighter. So I'm gonna do that now. I'm gonna make it brighter and dimmer because one direction makes it brighter, one makes it dimmer. So you see what I'm talking about? It does become brighter and dimmer based on how much you turn the potentiometer knob. Okay, the next thing I want to show is this. So this is a photoresistor, and this is interesting because this thing has more resistance. Sorry, I'm trying to remember. Yes. So this has resistance as long as there isn't any light hitting this surface with like these squiggly lines. As long as there isn't any light hitting this surface, it's going to have crazy resistance. And as you start bringing more and more light to it, the resistance goes down. So to demonstrate this, I don't know what's a good way to demonstrate this because I have to. So first of all, I have to wire it up. I'm just going to do that. But also, in order to demonstrate this, hold on. I don't know if you can make out uh, where this photoresistor is. So I'm just going to point to it. It's here. So that's the photoresistor. I need to move that to the other end just so my hand has more space to kind of cover the photoresistor. And then I'm going to change the wiring of the LED, that same red LED. And you'll see as I cover this resistor with my hand, the LED becomes dimmer. And once I release it, it becomes, oh, once I remove my hand, I mean, it becomes brighter. So give me a second. I need to set up this connection. Okay, so for the sake of, I forgot what I was going to say. Oh, for the sake of being able to have the potentiometer on like one edge of the board, I'm using these power rails, the blue and red power rails. So you can see the connection going from here to here and also from the microcontroller to here. So now watch as I put my hand on the photoresistor to cover it up and block out light mainly. Notice how the red LED becomes dimmer as I do that. In fact, I think I'll turn off this lamp that I've set up just so you can see the light. Actually, no, we're gonna need light in order to actually, activate the thing. So I'm gonna leave the light on. I hope that was visible. Let me see what it looks like on stream. Yes, yes, you can see it. So as I cover the photoresistor, you can see the LED becoming dimmer, and then once I let it go, then it becomes bright again. So this is great. We can play around with this as well. This is interesting because now we are starting to play around with components and circuits that interact with the real world, like the potentiometer, for example. It requires you to physically interact with it and turn it in order to change the resistance. And with the photoresistor, it requires or it reacts rather to darkness or brightness, which is we can use this. We can definitely use this for. I want to try using this for robotics stuff. I'll have to see in what way it is useful. Definitely, there's going to be a lot of like darkness related situations. I might actually try to order more of these because there are certain systems that I want to build. Like there was something gardening related that I wanted to build that I would prefer if it just powers down whenever it's night outside. So if the device is going to be kept outside, I can have I can put um, if the device is going to be kept outside, I can have one of these photoresistors in there, and depending on how light or dark it is outside, it can it can signal to the ESP32 that whether it should power down or go into like an incredibly low power mode or sleep or whatever. I mean, alternatively, I could also just do it based on the time of the day. I don't know how accurate the time of the day would be, though. I haven't fully understood how that is working in the ESP32. I need to look into the real time clock mechanism, how it's working, how accurate it is between reboots of the ESP32, let's say. Because I don't fully understand. Like, imagine we've set up the ESP32. We've loaded a program onto it, okay, and then we power down the ESP32. Not even low power. We've shut it off, right? For whatever reason, it gets shut off. Maybe we purposely shut it off. Maybe the power disconnected or battery ran out or whatever. The thing is off, right? How is the clock continuing to count? Like, are we going to get accurate results from the real time clock after we switch it back on? If so, how? What exactly inside it is counting such that we are able to maintain an accurate clock? I feel like I should ask this question to Gemini. Give me a second. Let me open up a new conversation in Gemini. Hey, I'm learning no STD, um, no STD Rust for ESP32. I'm still relatively new to the ESP32. I have done a bit of ESP32 MicroPython in the past, so I have a tiny bit of experience with it. I never understood how the real-time clock functionality works in the ESP32. How exactly is it syncing properly between reboots, power downs, possible crashes, and so on? Or have I just misunderstood how the RTC is working? Okay, it's a common point of confusion. Coming from MicroPython, the underlying hardware can feel a bit like a black box because the VM handles so much for you. In the no STD world, you're closer to the silicon, so understanding the RTC real-time controller, I thought it was real-time clock, oops, is vital. The short answer is the RTC isn't just a clock, it's a tiny, semi-independent computer inside your ESP32 that almost never turns off. The always on domain. The ESP32 is divided into several power domains, while the main CPU that survives, what? I think I skipped something. While the main CPU, Extensa or RISC-V, and the Wi-Fi slash Bluetooth radio drink most of the power and get shut down during deep sleep, the RTC domain stays powered on. The RTC memory. This is a small amount of fast SRAM, usually 8 KB, that survives deep sleep and soft reboots. In no STD Rust, you can use attributes to store variables here, so they persist even if the main program restarts. Then the RTC timer. This is the actual counter. It doesn't care if your main code crashes or if the CPU is power gated. As long as there is electricity hitting so and so pin, it keeps ticking. All right. Handling reboots versus power downs. To understand how it syncs, quote unquote, we have to distinguish between different types of off. Deep sleep and crashes are soft resets. If your code crashes, as in a panic in Rust, or you enter deep sleep, the RTC power domain remains active. The timer keeps incrementing. When the chip boots back up, your code can query the RTC controller to see how much time has passed since the last epoch or boot. Then full power down, hard reset. This is the catch. If you unplug the battery or USB cable, the ESP32 RTC loses everything. Unlike a PC motherboard, okay, all right, so it doesn't maintain the RTC. Sorry, it doesn't maintain the real-time clock. Unlike a PC motherboard, a standard ESP32 development board usually doesn't have a coin cell battery backup specifically for the internal RTC. When power returns, the RTC starts back at zero. To solve this, most developers use an external RTC chip like the DS3231 with its own battery or sync with an NTP server via Wi-Fi immediately after booting. Okay, okay. So I guess this answers the question about whether I should be using the clock in the ESP32 to determine when to power down or power back up. And it seems like the photoresistor is a better option there, because if the specific conditions for power down are that the sun has gone down and it's dark outside, photoresistor will accomplish that. And I have to think of a way to get the photoresistor to make the ESP32 power back up, because unless there's two separate chips, we are still going to need the ESP32 to kind of power back on real quick, read the values from the photoresistor, and or get some analog input from the photoresistor rather, and then decide immediately what to do, whether to power back down or continue running or what. And it can do this like, I don't know, once every 3 hours or something. So we'll be saving a ton of battery, because something I wanted to do with that specific project that I have in mind, and it depends really on how I'm going to be approaching it, because I'm still not sure how I'm going to be approaching powering the thing. There's multiple things that I want to do with that project, but one of the main things I wanted to do is create a sort of timer activated sprinkler system. Not even a sprinkler system, a misting system. And I want to use a relay module to handle the controlling of that misting system. So I'm gonna have to buy the entire misting system, because after playing around with actually even after doing a bunch of research, not just playing around with a bunch of these components, but after doing a bunch of research on this, I've realized that I'm better off trying to go and buy a ready-made misting system, even if it's something really small, because I only have to. It's a balcony that I have to mist. It's not like a big garden. So if I can buy like a small misting system, or even something that allows me to spray, that's all I need really. Um, as long as I can have something like that that's electronically controlled, I can then control it using a ESP32 and a relay module. My problem is I'm not able to find one that is cheap enough So I need to see how to go about doing that, because summer is coming. And last year for summer, I wanted to set up such a system, but I wasn't comfortable enough with in my ability to do these various ESP32 projects. And there were a couple of other reasons because of which I wasn't able to get to it. Let's just say last year was not, it was not a good year. It was pretty shit. So I just wasn't able to get to it. This year though, things seem to be going well so far. We are almost at the end of the third month of this year. So I'm pretty happy that things are going well so far. Hoping they remain well so far. I'm also hoping that we have some growth uh, in the Twitch channel, in the stream, basically. There's well, not just in the stream, content creation wise, because there's a bunch of things that I want to do. I wanna post more to social media. I also wanna, well, I wanna post more content to social media. I also wanna start posting stuff on my main YouTube channel again. Additionally, in addition to the main content that I plan on creating for that channel, I also want to start doing vlogs again. But this time the vlogs are going to be aimed at my electronics projects, the various electronics related things that I'm doing, or what I've been learning, or actually both. It can be both. It can be robotics. Sorry, it can be the learning thing and the building thing. So I can be doing my hobby electronics projects. I can be doing robotics projects. I can be doing various types of projects now that I have like a massive catalog of multiple different components and modules and various parts and stuff that I've bought over the years. Finally, now I can just start building shit. So I'm excited. I'm excited for that. Um, that being said, I want to read up on potentiometers. So I'm going to ask Gemini a question about this, and we're going to see what Gemini teaches us. Hey, so I'm actually, should I mention the ESP32? Okay, so I'm new to hobby electronics. We're gonna try a different, much simpler prompt. I'm not gonna mention everything to Gemini, so hopefully Gemini keeps things simple. The thing is, with potentiometers, when they're being connected to a microcontroller, a lot of times they even use the third leg of the potentiometer, because that's where the whole voltage divider logic comes in. So if I want to be able to use that, I need to mention the microcontroller. And additionally, oh, you know what I can do? Okay, so uh, I'm gonna write it like this. Hey, so I'm new to hobby electronics. Actually, I'm not entirely new, to be honest. I'm not entirely new. Hey, so I'm okay. I'm yeah. Let me just say I'm learning hobby electronics. I'm currently learning no STD Rust for ESP32, and I have an ESP32 along with, and dude, should I be giving this entire like backstory? I don't know. I don't think it's okay. Okay, I'll give, just to give some context. I have an ESP32 with an LED, resistor, and potentiometer, bracket trim pot, connected. Teach me about potentiometers. I don't know anything about them. Um, I, oh, with an LED resistor and potentiometer connected between D5, let's say, I think D4. Yeah, between D4, or let me make it simpler, a GPIO4 and ground. Teach me about potentiometers. I don't know anything about them. I mainly know that they allow you to create variable resistance, and they can be used as a, no, they are basically a voltage divider, but I don't really know anything about voltage dividers either. So my knowledge is close to nothing on this. Teach me. Okay, it's awesome that you're diving into no STD Rust with the ESP32. That's definitely jumping into the deep end of the pool, but it's great. It's a great way to learn how the hardware actually breathes. To understand why a potentiometer is useful for your ESP32, we have to look at how it manipulates electricity. What is a potentiometer? At its simplest, a potentiometer or pot is a variable resistor. Inside Inside the casing is a resistive track, usually made of carbon, and a sliding contact called a wiper. As you turn the knob, the wiper moves along that track. Okay. Oh, wait, that's interesting. Wait, so I'm assuming that one end or both ends of that track are the two legs in the potentiometer, because a pot usually has three legs. Um, I'm assuming the track is like the left and right leg, and then in the center is the leg connected um, to wherever you want, some kind of variable resistance to go to. So as you are turning the wiper, let's say you're turning it away from the left leg, the track kind of lengthens. This is my assumption of how it works, but I'm assuming the track kind of lengthens as you turn the knob, and because the track is lengthening, the resistance increases. Carbon conducts electricity, right? I'm assuming. Yeah, I think it does, doesn't it? I think it conducts it to a certain extent, which is how you introduce resistance into it, into the current. I think so. I'm not sure. Let's continue reading. As you turn the knob, the wiper moves along the track. If the electricity has to travel through more of the track to get to the wiper, the resistance increases. If the path is shorter, the resistance decrease. Words. The resistance decreases. Okay. All right. So let's try this out, because I currently have. Hold on. I need to. Okay. So I currently um, have this potentiometer, and I'm going to turn this to sort of try and understand like what direction, because like, okay, we have the two legs on the upper side and the one leg, which is the quote unquote middle leg, at the bottom. That's how this thing has been set up. So you can see that's why I connected the orange wire to the bottom and the blue wire to what we could consider the top left. So I'm just imagining this as like an arc of some sort, and um, just imagine you place a needle on like the left side of the arc, and then you just kind of turn towards the right side. So as you're traveling along that line, as the distance becomes longer, the resistance increases. I'm assuming because the current has to travel longer. But as you decrease the distance, the resistance also decreases. I think the thing confusing here is what side this is. Okay, let's try something. What I'm going to do is I'm going to turn this. Let me see what direction it's meant to turn. Okay, so now I've turned it completely to the left side. Um, Actually, okay, I've turned it completely to the left side. What I'm wondering is, okay, if I turn this, does that mean that the resistance is closer to the leg that's on the other side, the leg that's not connected? As in, no, the wiper's contact. Does this mean that the wiper's contact is closer to that end, meaning that we have a high amount of resistance because of which we don't see the the LED being that bright. So now if I turn this on camera, it's going to be turning towards the right side. So if I turn this, the wiper will kind of it'll take its full round and go to the left side. And because I have the wire connected to the left side, so as the wiper distance from the contact shortens, I'm guessing the resistance also decreases. And because the resistance is decreasing, the LED will become brighter. I hope I'm getting this understanding correct because, oh, you know what I could do? I could look up what trim pot internals look like. Do we have any images of that here? Yeah, so this is the kind of arc I was talking about. My assumption here is that as this wiper comes closer to this side, let's say we are not touching pin 3. So this is pin 1, 2, and 3. Let's say we are not touching pin 3. How well are you guys able to see this on stream? Give me a second. Yeah, yeah, you can see it. You can see it. Hopefully you can see my mouse pointer that well. But yeah, um, we have pins 1, 2, and 3. 3 is what the wiper is connected to, or 3 is where it's one end of the wiper, and 1 and 2 are basically our strip. So let's say we are not connecting to pin 3, we are only connecting to 1 and 2, and the wiper is being turned towards the left. So as it's turning towards the left, the path between 1 and 2 is quite short. So I'm assuming that means the resistance will be less. And as we turn towards the right and move the wiper away from 1, the resistance increases. Okay, so now to test this out, uh, I'm gonna turn I'm gonna turn this clockwise, and I'm assuming that's gonna bring the washer close to close to this pin, because currently it's closer to the pin on the other side. Sorry, I'm trying to reach over to the breadboard uh, because the breadboard is a little bit away from me because my mic stand is well, let's just say my mic setup doesn't allow me to reach that easily. Okay, so I'm going to turn this clockwise now, and let's see. I'm assuming the resistance is going to decrease. And because of that, the LED is going to become brighter. So sorry, if my understanding of this is correct, oops, if my understanding of this is correct, uh, the resistance is going to decrease and the LED will become brighter. Yeah, so that worked. The LED is brighter now. Give me a second. I'm just seeing this on stream. Yeah, you can see the LED becoming brighter. So something else that I noticed. Now, if you look at this image, will this image become bigger if I... okay, let's see if we can look inside a trim pot. Okay, good. This is, so we have a thing here. Um, actually, can we see the inside of the specific trim pot that I have? Hold on. Um, give me a second. Uh, yeah, I'm not sure. I'm not sure if we'll get that. So I'm just gonna go with this. So this is the arc I was imagining. This is our middle leg. This is left. This is right. I'm looking at the third image right now. So this is our middle point, and then we have the left and the right. The left and the right are for this I'm assuming carbon strip, and the wiper, as we turn the knob, the wiper is kind of scraping along this. So assuming we have only connected these two, let's say we haven't connected the third pin, we've only connected pins 1 and 2, one of them going to ground, the other one going to, let's say, GPIO 2 or GPIO 5, 4, 5 in my case. As we turn the potentiometer, as we turn the knob, let's say it started out here, because this also is telling me, this is reminding me of something else as well. Or this is, there's something else that I want to point out that I've noticed, which I don't fully understand, but like, yeah, I wanna try and understand it. Uh, but okay, so let's say the pot is turned completely to the left, and usually there's like mechanical restraints that stop the pot from turning any further, so it'll end up going off the strip. So let's say we are all the way here at the beginning. There's like no resistance between, or there's like least amount of resistance between pin 1 and 2. And so we are in the situation that we are in right now, where it is it's conducting pretty well. There's barely any resistance there. The only resistance is coming from the 270 ohm resistor that I have connected, right? So the LED is fairly bright. Now, as we start turning the knob and going towards the right side, we have this entire path that the electricity has to travel, and I'm guessing that's what increases the resistance. Um, so something that I noticed was that past the halfway point, it doesn't seem to affect all that much, or maybe the effect is still happening, but it's so minuscule that we can't really make it out. And I think the only way for me to really test this out is to give it more voltage than it can handle, but then I risk burning out an LED. Because, okay, initially the behavior that I was observing was that once we go past the half point, let's say we are connected to uh, pin 1 and 2, and pin 3 doesn't have anything connected, what I initially noticed is that once we go past the halfway point, give me a second. Yeah, once we go past the halfway point, the effect, it seems like it's not really affecting all that much. Wait, there was that observation, but then I don't think that's completely. There was also another observation. Now I'm remembering and I'm wondering if I just said my observations wrong. But no, this was one of the observations. Let me test that out real quick. Okay, I think I might have been wrong about my observation. That was, I think I confused what my observations were. One of the other observations that I had that I definitely remember right now is notice this thing. This I'm actually able to reproduce it, so I know that I'm remembering this right. My previous observation that I was talking about, which um, like once you go past the halfway point, I'm not entirely sure if I had that observation correct, because the path that it has to travel is still getting longer, so it does make sense that the resistance would still continue to be affected. Now, okay, yeah, sorry about the confusion. I literally confused what exactly I was confused about. So, the other thing that I noticed is, notice this thing where, so I'm currently at like least amount of resistance, okay, with my current potentiometer. Notice how as I turn this knob, as I like just start turning it, the light suddenly dims, and then it has a gradual fall off, but there's like a very sharp fall off at the very beginning. I need to try and understand why that happens. Notice I'll do it a couple of times so you guys can actually see that happening. This is something I can actually reproduce. The other one, because I'm not able to reproduce it, so I'm wondering if I was just confused about that. Anyways, if I do remember what exactly I was confused about there, I'll repeat the entire thing. But for now, I'm going to demonstrate this thing. Okay. I it took me some time to get the screwdriver in there. Okay, so now I'm going to start spinning it. There it is. Did you notice how it suddenly just dimmed? I'm going to do it again. Yeah. I don't know if like you can notice it all that much, but like initially there's like a huge fall off right there. And then it's further from that point it's gradual. Hold on. Let me continue. Yeah. So to demonstrate that using this same picture that we have here, imagine we are connected to pin 1 and 2, and we are not connected to pin 3, and imagine we are currently touching this area, or the wiper from pin 2 is currently touching this area, so there's like least amount of resistance there. Okay, as I start turning the knob, what I notice is there's a sudden fall off. It's not gradual. there's a sudden fall off. The light very suddenly dims. Though, okay, this might not have anything to do with the potentiometer itself. It might have something to do with LEDs, because LEDs, they have like they have a weird, like, I shouldn't call it weird, but like, if you try to get it if you try to get it down to the math, you will end up in situations where you'll be confused about why the LED is behaving the way that it's behaving, and why you pretty much always need a current limiting resistor in series with the LED. I've had those kinds of situations before, and I think it yeah, I think this, what I'm experiencing here, might be the behavior of the LED and not the potentiometer, but um, I'm not able to observe this with anything else because I don't have anything else to test it out with. Though, though I might have something to test it out with, because we now have a microcontroller as well. So we can do analog reads using the potentiometer. That's what the first Arduino example was anyways. Oh, I've also been reading up on the Arduino. Hold on, not Arduino, the ESP32 HAL stuff, and more specifically ADC. So I'm gonna have to, in order to explore the ESP32, um, I'm gonna have to go bit by bit, like exploring the various different sections, because each section has a different thing implemented for it. Something I also realized yesterday, I don't know if I mentioned this on stream, but something I did realize is that the No STD training book is super out of date and incomplete. The information is just all over the place. If you want information about using ESP HAL, which is the No STD implementation of which is the No STD implementation of embedded HAL for the ESP32. If you want to look at examples of it, you are better off going to the the repo, the, what do you call it? You're better off going to the ESP HAL repo and looking at the examples folder, because they have like 10, 20, 30 plus examples there for everything from basics to advanced stuff. A bunch of different things that have been implemented, a bunch of different functionality that has been implemented in there. There's an example for a bunch of those things. They aren't even sticking to like simple stuff that I'm sticking to, or I should say beginner. I'm not going to say simple because it's far from simple for me so far. But what was I saying? I was saying something. Yeah, they have, so okay, they don't have something similar to the Arduino catalog of examples, but what they have done is they have shown how to do a bunch of different things. They have their own way of setting up the examples. I'm gonna put it that way. So they have created examples for various things that they thought would be important, and other than what is in the examples folder itself, you can also come to this specific docs page, this specific documentation page that has been generated. I'm assuming this has been generated. I'm not sure, or maybe it's been written. I don't know. I guess I'll find out later on. But yeah, you can come to this page and look up specific things that you are interested in. So, for example, I'm currently looking into ADC, so I'm gonna look for. Hold on. Where was ADC? ADC was what, under peripherals, or I mean, I could just search. Why am I trying to guess? Okay, it's under analog. ESP HAL, analog, ADC. Where was this in that list? Was this not in that list? Oh, analog. Okay, analog peripherals. So this is a slightly different way of exploring the ESP32, and I'm kind of glad that I have some experience in doing ESP32 stuff already. Otherwise, I feel like I would have been a tiny bit confused. So I'm kind of glad that I explored this the uh, from the Python side first, from the MicroPython side first, and now I'm exploring the Rust side of it. I feel like the ecosystem still has a lot more evolving to do before people who are brand new to the ESP32 are able to jump into it and just start learning ESP32 directly from Rust, directly using Rust. Though, if somebody is brand new to the ESP32 but not completely new to microcontrollers, maybe they might be able to get started with this directly because I mean, I'm trying to imagine in terms of loading up a program onto the ESP32, how different would this be from using the C++ method? I'm not going to talk about MicroPython because with MicroPython, you're not loading up the program. You are flashing an entire MicroPython firmware onto your ESP32, and then that firmware, which contains a MicroPython interpreter, that interprets your scripts. So that's what's running your scripts. You're not flashing a new program onto your ESP32 each time that you run a program, but you are flashing it each time you run a Rust program. I'm assuming it's the same thing with the C++ version as well, because both of these are compiled languages. MicroPython and Python in general is not. Okay, all right. Moving on to this, what I was talking about. So I was mentioning the examples, right? So each of these specific modules. So under analog, we have ADC and DAC. DAC is digital to audio converter, and ADC is analog to digital converter. So for us, we are looking for analog to digital converter because we are trying to get analog signals. We are trying to read analog signals, and also, yeah, that's a good way. That's a good way to put it. We are trying to read analog signals from the outside world, and we're also trying to write analog signals to the outside world. So that's where we have analog read and analog write. So, okay, back to what I was saying. Each of the, okay, to be fair, I haven't looked at all of the modules. I could be wrong about this, but what I was about to say is that each of these modules, they'll contain examples as well. So you're not limited to what's in the ESP HAL crate. You can like explore these as well. You can explore you can come to the docs page for ESP HAL, and each of the modules is going to have examples for how to use the API. This is actually what we're going to be focusing on. And I feel like in order to explore and actually learn the ESP32, because so far I've mainly only learned theory stuff. There's When you go to explore the ESP32, there's you have the C++ side, and you have the actually, is it C or C++? I believe it's C++ being used. ESP32, C or C++. You can program using either C or C++, as both languages are fully supported by the primary development framework. The choice largely depends upon your project's requirements and your personal preference. Okay, C++ for the ESP32. C++ is an excellent choice for the ESP32, which is a powerful chip capable of handling object-oriented programming without performance issues. Arduino framework also uses with the popular Arduino environment for ESP32 is built on C++. It is great for rapid prototyping and leveraging a vast collection of community libraries. Then ESP IDF, which is ESP IoT Development Framework. The official low-level Espressif framework supports C++. Okay, all right. Then there's also, it's mentioned the benefits of C++. It says C++ allows for modular, structured, and reusable code, making it suitable for complex and scalable projects. Then C for ESP32. C is also a robust and highly efficient option, particularly for low-level or resource-critical applications. Performance. C is often seen as the standard for performance-critical embedded applications where every clock cycle matters. Direct hardware access. Using C often provides more direct control over hardware register. Why? Hold on. Why did I get stuck on this? Hardware registers. There you go. I think it was the way that I was saying registers that kind of made me get stuck there. Hardware registers. Fine. Control over hardware registers, which is common in professional industrial development, where highly optimized bare metal code is preferred. ESP IDF core itself is primarily written in C and provides C APIs, meaning C code integrates seamlessly and directly with the underlying system. Okay, okay. I at this point forgot. Oh yeah, I was talking about C++ because I was mentioning about when you go to look up ESP32 related details, like ESP32 development related details, in their documentation they have documentation for the C++ side, and they have documentation for the MicroPython side. If you are trying to learn about the various moving parts of the ESP32, you should be reading through those sections because they because you're going to be programming those various sections. So the documentation is kind of divided up in that way. So it explores various concepts, ADC, the DAC, and Wi-Fi and Bluetooth, and your general purpose digital pins, your analog PWM stuff, your RTC, and various other things, touch capability, various such things. It explains like the various. Why am I just talking about this? I can look it up right now and show you guys. Give me a second. I'm gonna open up both of them so I can show it on stream. Okay, ESP32 docs. Okay, so there's a programming guide from Espressif, then ESP32 MicroPython docs. And this one is from MicroPython specifically. Okay. Oh, yeah. Sorry, zoned out for a second there. Okay, OBS seems frozen. Give it a second. I think we're good. Hopefully we are good. Yeah, we're good. Okay. Right. So, this is the C++ side. Where was it? Was it in hardware reference maybe? Chip dataset, API guides, security guides. Standard I/O. I'm trying to remember where the thing was. The specific thing that I was looking at that kind of, okay, let's look at getting start or get started. That'll probably point us in the right direction. Build your first project, command line, okay. API reference. This might have been part of it, and then there's also the hardware guide, which might also have been part of it. Let me look at peripherals API. Yeah, this is it. This is it. So this shows you the various moving parts in the ESP32. This is just a peripherals API. There's a bunch of other. Hold on, this thing isn't. I can't scroll back up. Uh, okay, there. So they have like the Bluetooth API. They have the networking API, APIs. In fact, give me a second. Let that load. Yeah, so here they show you how to use various Wi-Fi related stuff, Ethernet. There's something threading related, which I didn't know was even a thing. At some point, somewhere here, Bluetooth gets mentioned as well. I don't remember where. Wait, no, Bluetooth has its own API. Sorry, Bluetooth has its own API. Um, that is here. And they also have other stuff like storage related stuff. There was somewhere here, they also, yeah, there it is. SD, SDIO, and MMC driver. So you can use this to interact with an SD. I don't know if you can use this to interact with an SD card directly or within, or if you're meant to be using an SD card module. It's one of those two, but yeah, you can do that as well. And this is how you learn all about the ESP32 hardware itself. Through these APIs, you get to learn that, oh yeah, um, there's these different things that you can do with various pins, and actually various pins on the ESP32 are multi-purpose. Some of them are like if you look at the data sheet, it'll mention that um, this pin, it supports, I don't know, SD this and GPIO that and touch this, and that sounds wrong, but touch whatever, and maybe something is ADC, maybe something. Each of the pins, they tend to be multi-purpose. You can use them for various different purposes, which is great because this allows you to this means that even if you have one of the smaller ESP32s, by the way, I just realized that so far, multiple times I've spoken about really tiny ESP32s, like ESP32 C3 Super Mini, for example, that I ordered maybe a year back. I don't remember. So far, I've spoken about it. I was never able to show it because I very recently started doing um, the webcam streams. I'm going to show it to you guys now. So currently on the screen, you are able to see the ESP32, right? I'm going to place the ESP32 C3 Super Mini next to that ESP32 for reference. Look at that. Look at that size difference, dude. That is insane. That is crazy. This thing is tiny. When I was saying that these things are tiny, I was not exaggerating. These are tiny. Look at this. This is like 1/3 of my index finger. That's how tiny these things are. The USB, I think Type C, I don't remember what it is. The USB Type C port is the USB Type C port itself is maybe, I don't know, 1/4 of the entire chip, 1/4 of the entire development board. That's how small these things are. These are tiny. These are crazy small. Like, holy shit, dude, this is insane. I'm excited to play around with these as well. Uh, I've ordered a bunch of them over time, but I never managed to test any of them out because I uh, I couldn't get around to soldering header pins onto any of them. And I'm kind of glad that I didn't I didn't attempt to install headers on either of them because, dude, the components on these boards are incredibly tiny. I'm not even kidding when I say the components on these boards. I can't show it on camera either. That's how small they are. The components on these boards are smaller than a grain of rice. They're closer to a grain of sugar or salt. That's how small some of these components are. There are bigger ones as well, but there are incredibly tiny components on these boards. So I want to be super careful when I'm soldering something onto it because I don't want to accidentally push something out of the way and then the board is just not going to work properly after that. So I need to be like super careful with I need to be super careful with how I go about soldering stuff onto this. Okay. So this is, yeah, dude, this is, yo, I'm excited. I'm excited. Um, I'm excited to explore more, a lot more, in fact. I'm super excited to explore a lot more electronic stuff, a lot more ESP32 stuff. I need to make sure that I'm balancing this well with with the polar stuff because I do need to make progress with that. Um, I'm kind of glad that I've decided to make polars a part of my content pipeline project because that's kind of going to force me to do polar stuff. But yeah, dude, we are now making progress with both electronics and the ESP32. Um, I need to. I think I'm gonna even off stream. I'm gonna continue learning about potentiometers. It's not potentiometers specifically that I'm curious about because I kind of understand the basic working mechanism here. What I'm really trying to learn about is using all three pins on the potentiometer because that's where you have the voltage divider concept coming in. And I don't know anything about voltage dividers. So I want to see what the circuit looks like and how the circuit behaves when you have a voltage divider in place. How a voltage divider works, what it does, what's the effects of putting one into the circuit, and stuff like that. That's what I'm trying to understand. And a potentiometer just so happens to be the perfect thing to learn about voltage dividers. But other than that, I've kind of understood the basic operation of a potentiometer and how we can introduce variable resistance into our incredibly simple circuits. And as an added bonus, we also learned about photoresistors, which are light activated resistors. Actually, they're not light activated resistors. They are there was a specific name for them. I think LDR, light something resistance. I don't remember what exactly that was. Hold on, I have the conversation open here. LDR. LDR is um, hold on just a second. LDR resistor. A light dependent resistor. Okay. So not I shouldn't say light activated resistor because that sounds wrong because that makes it sound like the resistance increases as the light increases. But here the resistance decreases as the light increases, and as the light diminishes, the resistance increases. I need to also see what kind of resistance these things have, because at least at least from what Gemini was telling me, they apparently have resistance in like the mega ohms, which I believe is like a million ohms, millions of ohms. And in terms of low resistance, when you have a bright light, their resistance can go down to anywhere between 50 to 1,000 ohms. So if that is the case, then I don't think I'm going to be looking for too many different types of photoresistors. But still, I mean, there might be like very highly precise photoresistors. I'm not sure. But yeah, we made some pretty good progress, and I'm excited. I'm excited for continuing learning electronics stuff on stream. We'll see what we're gonna look into tomorrow, because I'm gonna finish doing the photoresistor thing. No, the potentiometer thing today. Oh, tomorrow we can actually get into. Hold on. Tomorrow we can actually get into this, the ADC. We can read this. There's very few things to explore here, which is a good thing. In terms of ADC, there's just a couple of things we need to explore. There's a nice example given here as well. We can set something up and play around with ADC. There's I don't know where the read and write functions are. I think it's for the ADC pin. Hold on. So we enable the pin, we do add new peripherals.adc1. What does add new return? So we have the module here. In here we have ADC, then we have ADC pin, and okay, which can be read using the ADC. What about writing? Yeah, that's a good that's a good point. How are we doing writing? Okay, I guess we'll explore this more later on. Uh, there is clearly there is clearly a lot to explore in terms of the ADC. But for now, I need to end the stream. I'm gonna look for someone to raid. You know what? We are gonna go to Louise, because Louise is cool people. Louise is always chill. Um, we're gonna go hang out in Louise's stream. So I'm gonna set up the raid, and yeah, dude, we're gonna do another electronics stream tomorrow, hopefully. And we are finally making progress with electronics and with the ESP32. Hopefully soon, we're gonna start doing projects, ESP32 projects, robotics projects. I have a bunch of robotics related parts and stuff that we can play around with. Um, yeah, that's gonna be it for today's stream. I hope you guys have a nice day, and I'll see you all next time. Peace.